Derive the rate balance equation for a closed system operating at steady state. So we have a closed system, and if you are operating it at steady state, you can have some flow of heat into the system as well as a rate at which work is being transferred out. You can derive this equation right here. How do you derive that equation? Start with the Exergy balance equation for a finite process, going from state 1 to state 2. This is our equation that we had before, so you could have entropy transfer with heat. You could have full work, which included both shaft and the boundary work, so you subtract off pushing back the environment in case the system expands. V2 is greater than V1. And then you subtract off any exergy destruction due to entropy production. So take this equation, divide it by delta T. What's delta T? Change in time from the initial to final state. Divide the whole equation by delta T, then take the limit as delta T goes to 0. Those differences turn into derivatives. And then you say, well, it's steady state, so the rate of change of exergy in the system, 0, because it's steady state. This turns into a Q dot. That turns into a power. This is steady state, and then you have exergy destruction, so rate of entropy production. So there you go. So we have a wall in which heat conduction occurs, and the wall is the wall of an oven, and it has an inside side and an outside side, and it has air on the inside, and we're going to say it's very hot. It's 125 degrees C. The inside air temperature is hot. So let's put a temperature scale over here, temperature, put degrees C and put 125 there. The inside wall surface temperature is 115 degrees C. The outside wall surface temperature is 35 degrees C. Outside air temperature is 25 degrees C. So if you wanted to sketch a temperature profile through the wall, let's say this is X, you would say that out here it's 125, right at the surface inside it's 115, right at the outside surface it's 35, and then the air out here. So if I wanted to sketch a temperature profile, typically you go like this because of convection. There's a strong temperature gradient near the surface. Then a linear profile through the wall because of conduction, heat transfer. And then another dropping off like that into the air because of convection. The amount of heat transfer is steady throughout this system. I'm just trying to show it as a bunch of arrows. And Q dot, the rate of heat transfer, is always 1200 watts. No matter if I have a surface here, surface there, surface there, surface there. It's just a steady transfer from the inside air to the outside air through the wall of 1200 watts. Determine the exergy destruction inside the wall from the inside wall surface to the outside wall surface. So we introduce a control volume, which is right here. The left side is the wall surface on the inside. The right side is the wall surface on the outside. And we do an exergy balance. It's steady state, so 0 is equal to, we have some exergy transfer with the Q coming in on the left side. And that's a rate at which exergy is being transferred in on the left side minus the rate at which exergy is transferring out on the right side. There is no work being done. So you could put minus exergy transfer with the work, say that's equal to 0. And then we have any rate of exergy destruction. So we want to calculate this E dot D. Well, it's simply this term minus that term. Well, what is that term? It's 1 minus the dead state or environment temperature divided by the temperature on the left times Q dot minus, and then what is the rate of exergy transfer on the right? 1 minus T naught over the temperature on the right times Q dot. Are these Q dots the same?
Yes.
Same. It's all 1200 watts. That's right. Are these T naughts the same?
Yes.
Those T naughts are the same. That's the dead state temperature. Often they give it in 25 degrees C. You have to make sure and put that into Kelvin, so it's 298 Kelvin. What is that temperature in Kelvin? Well, a lot of times I'll just go ahead and convert Kelvin right away. Do it once. Hopefully don't make an error there. So this is 398. This is 388. This is 308. And this is 298. So that temperature on the left for this problem is 388 Kelvin, true? How about the temperature on the right? What is that temperature for that control volume? 308. And so when we crunch through the math, we find that the exergy destruction rate is the difference between the 278.4 watts coming in on the left side minus the 38.96 watts going out on the right side. Hence the exergy destruction rate inside is 239.4 watts. That's the answer for part A. What about part B? The exergy destruction in an enlarged control volume. Often they do have enlarged control volumes when you do an exergetic analysis. Because if you push out with a large control volume, let's say I'll try and color it green, out to this. Okay. Now I have the exergy transfer coming in across this surface, but that surface is at 398 Kelvin. And I have the exergy going out across this surface, but that temperature is 298. So you do the same type of calculation, and you'll find the exergy destruction rates, exergy transfer in 301.5 watts minus 0 watts. Hold it. I have 1200 watts being transferred out over this right surface of this extended control system or control volume, right? With all that 1,200 watts, there's no exergy transfer with it? That's right. Because it's at the dead state temperature. It's at 298. So the rate of exergy destruction is 301.5 watts. Is it larger for the enlarger system? Yes. Let's move on. You can also have the exergy rate balance equation for a control volume for an open system. Now, you can develop a very general equation. It would look like this. In a minute, I'll talk about giving you the option to see a derivation of an equation like that. But just let's look at the equation and see if we can understand it. I have a system. It's a control volume. I can have some heat transfer into that system. I can have some work out of that system, out of the control volume. I could have some mass flow into the system, and I could have some mass flow out of the system. Okay, so the first term over here says this is the rate at which the exergy inside the control volume changes with time. If it's positive, that means it's accumulating. If it's negative, it means it's decreasing. But it's how the exergy inside the control volume changes with time. Well, one way that it can go up is there can be an exergy transfer with the heat coming in, bringing it in. Professor, what happens if we had some heat transfer on this side and some heat transfer on that side? Well, then put a summation there and sum them all up. Wherever it's coming in across the boundary, you have to know the boundary temperature and the dead state temperature. Okay. And then the exergy can flow out with the organized energy transfer known as power. There's no factor here that's 100% times W dot. This in the parentheses is always less than 100%. It's some Carnot efficiency. Okay. What is this term? Very rarely is that term anything but 0, because this means right here, the volume of the control volume, how does it change with time? Is it continually expanding with time? That's rare that we would have a problem like that. But if you did, you would want to include that term, because it's continuously pushing back the boundary at pressure P naught. So that's non-useful work, so subtract that off. All right. Then we have, actually, this probably messed up on the subscripts. I have to include that term in there and then subtract it off. All right. This is a mass flow rate with the flow exergy in. This is the mass flow rate with the flow exergy out. What? It's a different exergy. It's a flow exergy. It's just like enthalpy was a flow energy. It accounted for the flow work. We have a new exergy. It's called the flow exergy. And then you have exergy destruction. Now, I don't think there is one problem in the textbook that requires you to analyze a transient exergy balance problem. So we all analyze steady state. As soon as you say steady state, that term and that term are 0. True? Steady state. That simplifies life. So here we have exergy transfer with the heat, exergy transfer out of the control volume via shaft. We have also our mass flow rate. If it's steady state, that mass flow rate's the same as that mass flow rate. And we just have a change in the flow exergy. I have a single inlet and a single outlet. And then we have the rate of exergy destruction. Does that equation look useful? Does it look okay? You can read it? All right. How would you derive this steady state exergy rate balance equation for a control volume with basically one heat transfer that's in, one work out, and a single inlet, single outlet, so your M dot's the same? How would you derive that? We could derive the more general equation, but then it's really tedious. How about if we assume some things up front and then try to derive an equation that's simpler? Well, you would start with the derivation with an exergy balance equation for a closed system that distorts over some time. And you would then write it carefully and then take a divide by delta t. So you divide this equation by delta t, delta t, delta t, delta t, and you would get this term would go away because of steady state. This term would go away because of, actually that one would not go away. There's two pieces out of this that I need to keep. This turns into a Q dot, and then what happens is you pick up a flow exergy. You pick up a flow exergy. Well, so in that derivation, you naturally are going to introduce a new variable called the flow exergy. How many people would like to see that derivation? So we said we're going to start with this equation. That applies to a closed system that's going to deform. So what you do is you have a control volume that looks like this round thing right here. But you have an inlet pipe and an outlet pipe. See how I've shown it? And what you have to do is you have to pick a pack of fluid that completely fills the control volume plus is about ready to flow into the control volume over the next time step delta t. So that initial mass is shown by the green dashed line. Can you see that? That green dashed line. It kind of goes here. Sorry about that. But it extends into the pipe where the flow is going to come into the control volume over the delta t time from initial time t to time t plus delta t. When it does, you also have to push out some fluid. So it's going to go out this pipe. So the distorted shape now is when it ends right there, it still has to completely fill the control volume, and it comes over here and is pushed out that exit pipe. If you get that concept down, you got 10% of the, you're in the right direction. Then what you do is you say, I have a imaginary piston or other fluid that's right over here. And what's happening is that fluid is pushing the other fluid, the green fluid, into the control volume. That's my flow work term. It's going to be my PV term. All right. Likewise, a little blue piston over here, and he's going to be pushed back by the fluid, the red fluid that's coming in. And so the initial place of the piston goes to the final place of the piston, and the initial place of this piston goes to the final place of that piston. Notice I did not try to draw them the same diameter. I did not try to draw them the same diameter. Because they're doing steady state, for the same amount of time, the mass that flows in is equal to the mass that flows out. All right. Otherwise, you'd have mass accumulation or depletion in the control volume. That's a lot of prep work. But now we say that initial state 1 is at time t. Final state is at t plus delta t. Got it? And now we say, okay, what is the exergy at time t? Well, it's made up of two parts. It's the exergy that's in the control volume at time t plus the exergy that's about ready to flow in, subscript I. What is the exergy of the new distorted system at time t plus delta t? It's the exergy in the control volume. Remember, the control volume is only this amount right here. See, it's only that. That's the control volume. This pushing in and pushing out helps us get the right energy balance and exergy balance. Okay, so it's that plus what flows out. What flowed out. Okay, and then I quickly expressed them as M times E, where E is our traditional non-flow exergy. Okay, then over here we work on this term. You say, I'm going to have it for a time increment delta t, have T naught and B be constant over the time increment delta t. This is just delta Q, how much heat is transferred, minus a little bit of shaft work, so Q in, a little bit of shaft work out of the control volume over the time step delta t. This total work, see how this term had this boundary pushing in and out? What you have to do for the total work is you have to conclude the work that the system does pushing this piston back, exiting. And you have to then, see that's a minus sign, so we're including it just like it's a positive work out. And this is the work that the system receives from this piston pushing it in. So the signs are correct. This one is a positive, that. And then you say to yourself, that amount of work is a PdV. It's a P, pressure, times how much volume was swept. That pressure, we're going to just, because of small time steps, it's not changing the pressure at the outlet. It's also steady state. It wouldn't be changing. The pressure at the exit would be different than the pressure at the inlet. That can still be true. But the volume swept is the product of the mass that gets pushed out times the specific volume of the fluid that's going out. True? Isn't that cap V exit? Likewise, this is equal to pressure on the inlet, mass inlet, specific volume on the inlet. You can start to see that PV term show up. All right. Now, this other term, P naught times the change in the volume, this volume is the volume of the control volume at time t plus dt plus the volume that is about ready to exit the system. That's this volume V exit. That volume V exit, we just already expanded it. That's equal to the mass exit, specific volume exit. Okay. Likewise, this volume inlet, you have to account for here. All right. And that volume we already did. That's the mass inlet, specific volume inlet. And then finishing out, you have this entropy production times T naught exergy destruction term. Look good? All right. Now at this point, these two terms over here with the red, I'm showing you something that cancels right away because we're assuming steady state. Otherwise, it takes a lot more tediousness. It takes me 2 pages, 3 pages to do it. Likewise, the volume of the control volume doesn't change. This control volume doesn't change. So this red strike, those two terms, greatly simplifies the math if we employ or assume steady state right there. Now, what we do is we take like this term and group it with this term and group it with this term with that P naught right there. And so you're going to bring that term over to the other side. There's just algebra here. 0 on the left-hand side is equal to nothing with the heat transfer, leave it alone. The shaft work, leave it alone. But collect everything that multiplies m sub e. Everything that multiplies m sub e. It's the exit exergy plus PV on the exit minus P naught V exit. And then to group everything that multiplies m in. Okay. And you notice that the exergy plus PV minus P naught V can be rewritten, it's just algebra, as H minus H naught minus T naught, S minus S naught plus KE plus PE, and you call that, you define it to be the flow exergy. There's a lot of tedious algebra there. Okay, you divide every term by delta T, take the limit as delta T goes to 0, you get a Q dot, you get a W dot, you get an M dot, and you get a sigma dot. And there it is, QED. Let's solve a problem. Steam at 3 kilogram and 80 bar and 440 degrees C enters a turbine. It exits at 20 kilopascal. That's a low pressure. The turbine isentropic efficiency is 85%. Determine for part A, before we get to B and C, what is the power out of the turbine in kilowatts. So you have your turbine, inlet state 1, exit state 2, and you have W dot, the power out. Is that what we're asked to calculate? What is the power out of that turbine? Is that part what we're W dot T? All right. Nothing to do with this class. Everything to do with the prerequisite class. All right. We introduce a control volume around the turbine, and we do a first law analysis. Okay. And we probably want to organize our results in a table. So strongly encourage you to organize results in a table where you'll say, okay, this is the state 1, state 2. This is maybe the pressure, and I got to pick some units. I like to pick kilopascal. The book likes bar. You can pick either one. You just have to make sure and not mess up unit conversions. The temperature in degrees C. Maybe there's a quality. Maybe there's a enthalpy. Maybe there's an entropy. Maybe there's a U and a V. I know I don't need them for this problem, but you could put U and V there as well. And then you could also now put E sub F, the flow exergy. If you put the flow exergy, I recommend you introduce state 0. It makes it a lot easier. So at state 0, the pressure right here is 1 bar. Can I convert that to kilopascal? 100. Can I 25 degrees C? Knowing the pressure and the temperature, I should be able to go into the steam tables and find everything. I should be able to find H and S. And then what is E sub F? Just it's H minus H naught minus T dot S minus S naught. I'm going to neglect kinetic and potential energy. That flow exergy at the dead state is 0. But let's go to state 1. They give me the pressure and the temperature, right? It's 80 bar. How many kilopascal is 80 bar? Is it 800? 8,000, I mean?
Yes.
Is it?
Yes.
Looks good to me. And then the 440 degrees C. Okay. Now I should be able to go to the steam tables and pick off the values of H and S. This is subcooled liquid, or state 0. This is superheated vapor. You have the superheated vapor table. Okay, the superheated table. Now I know that the textbook has a value. I use software and my value is very close to theirs, but if you try and compare, it's close but not the same. But I'm going to use this value for enthalpy and 6.5215 for entropy. Now, because I went and I calculated H to be 104.9, H naught, isn't this H naught right there? And S naught to be 0.3672. I can also just calculate the flow exergy of the inlet stream. It's 1308.4. I'm going to need that for part B and C. All right. Now we read the care problem and we say, this thing is isentropic efficiency of 85%. True? I've studied this before. Probably a property diagram will help me in my thought process. I'll introduce, and I'll just try and tuck it up here. Let me do this. Let me try this. Move this out of the way a little bit. And then introduce a property diagram right here, which is a, I have a lot of property diagrams to pick. But I'm going to be considering the isentropic efficiency of that turbine. So you suggest a property diagram. TS. A temperature entropy diagram. And probably it's going to be steam. It's going to maybe have some states that are in the two-phase region. So put the dome on. Right? And then I try to put a line of constant pressure that is 8,000 kilopascal, as well as another line of constant pressure that is 20 kilopascal. So put on two lines of constant pressure. The first would come up, cut across, and go up. The other one down here, lower pressure, go like that. So this one is the high pressure and the low pressure. And then we go ahead and find state 1. Theoretically, it's out there somewhere. There's state 1. And what we want to do is we want to consider isentropic expansion through that turbine first. So it's going to expand on a TS diagram straight down. True? And that'll go to state 2S. Is that true or false? You like that? So state 2S. So we're going to solve this problem in two steps. I'll consider expansion to state 2S, and then I'll consider expansion to state 2 actual. And on the diagram, 2 actual is either going to be to the to the right of state 2S, or to the left of state 2S, or the same location, vertical or horizontal location of state 2S. This is a great chance for a question. So we turn this on. And we ask that question. And do you understand the question? Answer if it's to the right with the selection A. Answer if it's to the left, selection B. And answer if it's straight down, C. You have A, B, or C. Where is state 2 actual? Is it to the right of 2S? Answer A. Is it to the left of 2S? Answer B. Or if it's right where it is with 2S is with 2 actual, then answer C. So a lot of people said it was mostly 75% said it's to the right. Now, what's the difference between the expansion from 1 to 2S? It's isentropic. It's reversible. It's the best expansion. You couldn't design a better steam turbine if you tried. It's completely reversible. We're not perfect. We can't make perfect machines. We're going to have some friction. We're going to have some irreversibilities. What's going to happen if you do have some irreversibilities? There's going to be some entropy generation. What happens to that entropy that's generated inside the turbine? It has to be swept out with outgoing fluid in addition to the incoming generation, incoming entropy. So S going out is higher. It's going to be off to the The actual, maybe it's right here, and maybe we show a dashed line going down to 2 actual, state 2 actual. Make sense? All a review of thermo 1. Now, how do I find or fix state 2s? Well, I know the pressure, so let's just put the pressure in, 20 kilopascal, and I need another property. What is my other property? Is it, here's a good, do I think I can get A, temperature, B, quality, C, enthalpy, or D, entropy, or E, flow exergy as my second property to fix the state 2s and able to calculate all the other properties? And yes, a lot of you are correct, because what is it? It's the entropy. C1, and that's why we like a TS diagram. State 2s is directly below. If it's a reversible expansion and there's no heat transfer, the turbine is not a heat transfer device, we assume it's adiabatic, S1 is equal to S2. All right, so let me do this. Let me make sure and select the right answer. D it is, and then we go away. So congratulations. So what we do is we put in, we just copy this number down, 6.5215. Now knowing pressure and entropy, the game is to get all the other properties. Try to get temperature, try to get quality, try to get enthalpy, try to get flow exergy. Got it? All right, this ends up being in the 2-phase region where the quality is 0.804. If it's in the 2-phase region and the quality is 0.804, what do you think the temperature is going to be? Now I'm not asking a question for the clickers. It'll be the saturation temperature. So Tsat, this will come in right around 60.1 degrees C. Yes, sir? Did you have a question?
Yeah, what about the 85%?
We're going to do that in our second step. So from 1 to 2, that's isentropic. And then the second, we'll use the information about the 85% isentropic efficiency. And so the enthalpy is, for this problem, 2147.2, and the flow exergy is 208.3. There's some steps, I run over them, that I did it very fast there. Now, we know that 2 actual is a little to the right of 2 isentropic, but it's on the same line, the same pressure line. It's still at 20 kilopascal, true? But what other piece of information do we use to fix state 2? Well, we go back to the definition of the turbine isentropic efficiency. That turbine isentropic efficiency is a ratio of the work per unit mass actually out of the turbine divided by the work per unit mass out of the turbine if it was isentropic expansion, S equal to a constant, which is H1 minus H2 actual divided by H1 minus H2S. And so we say, this is 85%. H1 is known. H2 isentropic we just found. Hence we can get H2. And so H2 comes in at 2312.2. So it's pressure and enthalpy that allow us to fix the state 2. If we go and check, we find that the quality is a little higher, 87.4%, meaning that this temperature, let me ask this question, the temperature now, right here, I'm trying to calculate this temperature at 2. Is the temperature at 2 going to be, I'm going to ask a clicker question, less than 60.1? That was the temperature at 2S. Is the temperature at 2 equal to 60.1? Or is the temperature 2 greater than 60.1? Answer A, B, or C. I turn on to collect your responses, and we see how you come in. And we show the results. And this is absolutely correct. So the temperature is the same because the quality is the same and the pressure didn't change. So B is the right answer. You could put your clickers away. No more time for that today. Thank you very much for participating. Now, so this is the 60.1. How about the entropy? You can look it up, and it's higher entropy, 7.0167, and the flow exergy, 225.7. So now that I calculated all that, what is the the power out of the turbine? What is W dot T? Is that the mass flow rate times W actual, which is H1 minus H2? Is that what it is? And yes, it is. And you calculate that the power developed by the turbine is 2805 kilowatts. What's the exergy destruction rate in the turbine? Well, we do an exergy balance for the same control volume, and it's steady state, so there's no heat transfer across the boundary of the turbine. You do have exergy flowing out with the turbine shaft power. Okay, we're going to have the mass flow rate coming in with the inlet flow exergy, outlet flow exergy, EF2, and we have exergy destruction. Did I write that exergy balance equation correct, or did I make an error in that? Did I leave out any terms? Looks okay. So the exergy destruction rate is equal to the mass flow rate times EF1 minus EF2 minus W dot T. You can read this equation. This is the change in the flow exergy of the fluid stream through the turbine from inlet to outlet. It comes in high, goes out low. Multiplied by m dot, that's a rate at which the fluid stream provided an exergetic flow into the turbine. Where did it go? We want it, as much of that, to go into the shaft power as possible and go out that way. What happened to the rest? It was destroyed. And so when you make this calculation, you find that 3247.8 kilowatts came from the fluid stream, between the inlet and the outlet of the fluid stream. We already calculated that 2805 kilowatts went out with the shaft power, meaning the exergy destruction rate is 4.2.7 kilowatts. What about the last one? What's the exergetic turbine efficiency? Well, this is the second law, turbine efficiency. It's something new for us. Let me try and tuck it in right here. If you had an exergetic turbine efficiency, it's really the ratio of what you wanted to happen, but you didn't get as much out as possible, over what was provided. Okay? What you desire or got out of it, if you like that word, got, okay, over what was spent or provided. So what happened is you had some flow of exergy coming out of that fluid stream. Where did it go? Where did we want it to go? We desired, or we wanted it to go, into the turbine shaft. Out, what we want out, over in. That's exactly right. I'm running out of room, but I'll just put it right here. You can calculate that exergetic turbine efficiency, often also called the second law turbine efficiency, to be a whopping 86.4%. Now you look at it and say, I learned in Thermo 1 the isentropic efficiency of a turbine. Now I have a different efficiency of the turbine. Numerically, they're not that much different, are they? 85 and 86%. But it's a slightly different meaning. Any comments or questions? Thank you for your attention.